Previously, we were looking at forced oscillations, and we defined and we looked at the conditions of forced oscillation. So let's quickly recall what we have studied in the previous class. So during an oscillation, the loss of energy will be there because of the oscillations being damped. Okay, if at all we try to compensate that loss by any external periodic force, right, we can make the oscillations to be sustained. We can make it to sustain, right? So under such condition, so if we have vibrations in which the body vibrates at a frequency which is other than its natural frequency, and the action of an external force, right, should be there. Okay, if these two conditions are met, I repeat, what are the conditions? First thing is that it should oscillate at a frequency which is other than the natural frequency, first thing. And the second thing is that, right, it should be under the influence of an external force. All right, so if these conditions are satisfied, we are going to call such oscillations as forced oscillations or forced vibrations. So till here we had seen yesterday. So now let's look at the theory and the analysis of forced vibration. So in case of a forced vibration, right, the body which is under forced vibration or forced oscillation is acted upon by the following. So the first force is that a restoring force. This is there for every oscillation or every vibration. So it's a restoring force, right? This force is always proportional to, we know that, displacement. So the restoring force proportional to the displacement, but what is the direction? But it is oppositely directed. Oppositely directed. All right. So we know that that particular force, we can denote it as that force F is equal to minus mu into y. So mu is the constant of equation and y is the displacement. That's the first force. Then we have a second force coming into picture. This is another force called a damping force. It's a damping force. It's proportional to the velocity, and that particular force is also oppositely directed. Correct? So this means this particular force is equals to, we'll put a constant, right, that is equal to r. Direction is reverse, so minus, into the velocity is denoted by dy by dt. So let me call the previous equation number 1, this is equation number 2. All the constants we know now. In addition to this, you see, we need one external force, and the external force is the one which makes the oscillation to sustain. So this is an an external force, right? This is something like it is basically represented by, right, a specific function. Okay, force, let's represent by, so capital F into, this is sine of P into T, because this particular function has a maximum value whenever the force is equal, right, at the frequency P by 2 pi. Okay, F sine pt. So here, let's try to write the details where the F is the maximum value and the whatever P we have written, so P divided by 2 pi is the frequency of this, and say P by 2 pi is the frequency. So you know that it's not simply represented by F, because the definition of these kind of oscillation, forced oscillations or forced vibrations, expect a periodic force. So I have to show that this F is periodic. That's why it is F sine pt, not simply F. Okay, therefore the total force system, right, is denoted by the following. That is, we can write an equation, right? M into this force is equal to ma, the total force that is actually generated internally by the particle which is oscillating. Okay, so this is m into d square y by dt square should be equal to minus mu times y. This is the component of the restoring force. Then we have a damping force that is denoted by minus r. This is dy by dt plus the external force that is F into sine pt. Okay, now what we do, we try to represent this system by the following notation. Let's take the component which has y to the other side. So the equation becomes m d square y by dt square. So this is plus r times dy by dt plus mu into y becoming equal to Cf into sine pt. So f sine pt has no y component, so right, we'll keep it on the other side because this is a function of t, right? We know that y is also a function of t, so we got a different function of t as a result. Okay, now let's divide both sides by m. Okay, so when we divide both the sides by m, we are going to get this. So m cancels from the first term. You simply have d square y by dt square plus this is r by m into dy by dt plus this is mu by m into y is equal to f by m into sine pt. Okay, now we know some of the constant here. We already have used them, right, in the previous type, that is a damped oscillations. So let's try to put them here. That is what we know. We know that the r by m is nothing but 2 times b. Okay, b is a damping coefficient, and the mu by m can be replaced by omega square, and the F by m, the force per mass, force per unit mass, we call it as, right, the small letter f. So this is capital F by m is f. So let's call this by another equation number. So let's see, I think we gave equation number 1 and 2. So this becomes equation number 3. Okay, and we call these set of equations by number 4 and substitute 4 right in the above equation. So this implies the d square y by dt square plus 2b into dy by dt plus omega square times y becoming equal to f into sine of pt. So call this equation number 5. Right? So again, this is a differential equation of motion of a particle. Right? Whenever this reaches a steady state, right, particle will vibrate with the frequency of the applied force, not with the given force. Okay, so we'll directly go with the solutions now. So okay, let's write this. Therefore, the solution of this kind of equation can be represented by the following technique. Okay, solution of 5 is in the form, let's write a form now, that will be a sinusoid, right, denoted by some amplitude a into sine of, the frequency remains same as the exciting function, that is f sine pt, has a frequency p into p. So right, that's a p term coming here, pt minus or plus, there will be a angle. Okay, it leads or lags. Normally it will lag, that's why it is minus theta, because as soon as you apply a external force, the effect of force will not be directly seen by the oscillating function, it lags by some angle, so that is why it is theta. So this theta is the lag angle and this a is the steady amplitude. Steady amplitude of vibration. Okay, now we try to write this function back in our original equation. Okay, that's original equation in the sense just now we wrote a function, right? So that will be denoted by equation number 5. We want to put the y over there, but I can see that equation 5 says not only just y, it is dy by dt and d square y by dt square. We have both the functions over there. Just to substitute the values, we need the differentiation of this. Okay, so let me call this equation by equation number 6. So let's differentiate this equation first. All right, so that means this implies differentiating with respect to time, I first get dy by dt. So you can see that this dy by dt is, a is a constant which remains there, sine of pt becomes cos of pt minus theta into p. So I'll write the p first, a p into cosine of the same function pt minus theta. And also if you try to find d square y by dt square, right, this is equal to, a is a constant, there is a p existing already, cos pt is minus sine pt into p, so there is one more p coming up, minus goes here into the sine of pt minus theta. So this means we have to use these two equations in 5. So let me call this 7. So using 7 and 6 in equation number 5. So just see that I replace dy by dt, d square y by dt square and the y in equation number 5 by using the equations we just got, that's 6 and 7. Okay, when you do so, we are going to get this. So there is a d square y by dt square, correct? So what I can do here, this is minus a into, this is sine, I think sorry, there is a p square, right? This is d square y by dt square. So I have to write the terms containing p square. A into p square into, this is sine of pt minus theta. This is d square, correct? Then we have a 2 times capital B into dy by dt. So dy by dt is a into p into, this is cos of pt minus theta, correct? Then I have the next term coming up, which is plus omega square into y. We assumed y as a into sine of pt minus theta, that is equal to the right hand side. Right hand side is f into sine of pt. Okay, so what I do, I make a small change on the RHS. Left hand side still remains same. Let's write this as f of, sorry, f into, my mistake. So let's write this f of, f into sine of, I add theta and I subtract theta. So I can write it as pt minus theta plus theta. So actually what happens here is that they will be cancelling each other and I'm still left with the pt which is there earlier. Okay, but since on the left hand side I have the pt minus theta as some of the terms, I can write it in this way. All right, now let us try to write the terms. Let's try to group the terms on the left hand side. Okay, so you can see that on the left hand side I have the terms. I can club these terms, omega square a sine of pt minus theta and minus a p square into this. Let's club them together. Okay, and when I club, I'm going to get the following term. So I'll write the positive term first. So there is a into, see, omega square is positive, omega square minus p square into sine of pt minus theta. So this term is what I'm getting from the highlighted terms in the previous line. Then I have the terms like, the next term should be the cos term which is there. So I'll write this is plus 2 times b. Okay, so I wrote a capital B over there. Kindly correct that and replace it by a small letter b. Small letter b. Okay, this is 2b, like this. So it's 2b. So 2b into ap cos pt minus theta. This is what is there on the left hand side. So right hand side, now we get a different one. So I can see that there is a sine of a plus b format. Okay, so where we can see this looks like a and the theta looks like b for us. So we know that sine a plus b is sine a cos b, cos a sine b. So we'll write the f as it is into, so this is sine of first function pt minus theta sine a into cos b cos theta plus f into, this is cos of the first function cos of pt minus theta into sine theta. All right, so we got an equation which almost matches on both the sides. So I can see that the terms are actually matching. So I can see that sine of pt minus theta and sine of pt minus theta which is there. Okay, and cos of pt minus theta is here, right? So remaining terms I can equate. All right, so let's do that equation now. So we can equate the terms which I have highlighted here. So that means I can highlight these two. So sine and sine are same on both sides. I have the terms. Similarly, you can see that cos pt and cos pt also do exist on both the sides. Okay, so if this equation is good for every value of t, that means the coefficients of sine pt minus theta and the cos pt minus theta should be same, correct? So that means, right, what do you mean by that? The meaning is simple. So this term, the coefficient of sine pt minus theta, should be matching with f into cos theta, correct? At the same time, the coefficient of cos of pt minus theta, that is 2b into ap, should be equal to f into sine theta, right? So whatever colors I'm writing, those colors should be same, because both green colors are same terms, both colors of cos functions are also same, right? So this indicates that I can equate the following terms. This implies, right, we can equate the coefficients of sine of pt minus theta on both the sides, as well as we can definitely equate the terms, right, which are the coefficients of cos function also on both sides, and the coefficients of cos of pt minus theta on both the sides. So you see that when you compare the coefficient of sine function, this is something like, you see, a into omega square minus p square should be equal to f into cos theta, correct? A omega square minus p square is equal to f into cos theta. Okay, and we have the second term, that f into sine theta becomes 2b into ap. Okay, so 2b into ap is equal to f into sine of the angle theta. Right, let's call them by separate numbers. I think previously we got the equations till 7, so this is, let's say, equation 8 and equation 9. So in order to get the exact term, right, we need to square the terms and add. Okay, so squaring and adding. Right, you see that on the left hand side I have a square into omega square minus p square the whole square, right? That's the first term. Second term also should be squared, so this becomes 2 square, so 4. B becomes b square, a becomes a square, and there is a p whose square is p square, is nothing but on the right hand side, this is f square cos square theta plus f square sine square theta, where cos square plus sine square equal to 1, and I am simply writing f square. Okay, now let's say I want to calculate the value of a. So this implies, let's write what is a square, right? Let's take the a square common from both the terms. Then I have omega square minus p square the whole square plus, this is 4 into b square into p square should be equal to f square, right? So now this means that a square can be calculated as f square divided by the omega square minus p square the whole square plus, this is 4 times b square p square. So this implies, now I want to calculate a means what? Take a square root. Numerator has a f square, so square root of f square is f, divided by denominator is not a perfect square, so I need to retain the square root. Then I write the terms as it is. Omega square minus p square the whole square plus this is 4b square p square. Call this as equation number 10. Also, this is how you calculate the amplitude of oscillation, capital A. And at the same time, let me say I want to calculate the theta now. So from 8 and 9, you can see if I divide 9 by 8, so sine theta by cos theta, which is there on the right side, gives me a tan theta. Correct? So I'm going to use that logic here. So this is equation 9 by equation 8 gives me. So there is f sine theta by f cos theta. So f cancels. Sine by cos gives you a tan theta. I'm going to write this directly. So tan theta is equal to, on the right hand side, I have 2 times b into p divided by omega square minus p square. Right? So this implies, how can you calculate a theta? Theta nothing but take tan inverse on both sides. That is 2 times beta p divided by omega square minus p square. So using this, I can calculate, this is equation number 11. So we can calculate the angle theta of the forced vibration. So how much angle is the delay angle or the lagging angle can also be calculated like this. Okay, now we have several cases coming up into picture, right? We'll look at the cases one by one. Okay, so this is, say, case number 1, in which we assume that the frequency of external force is lesser than the natural frequency of the oscillating body. So that is denoted by P is less than omega. Right? So we know that we already have derived the equation, so we can use them directly now. Right? So we know the equation for A, correct? So I'll start from there. So we know that, we already know that the value of A is, right, F divided by, A is equal to F divided by square root of, this is omega square minus P square whole square plus 4 into B square P square. So this implies, right, I know that the term P is much lesser than omega, right? So when P is lesser than omega, right, I can neglect the P here. So it's simply, I can write it as omega as the term, right? So this can be approximated simply to F divided by, now you see the term containing P can be neglected because P is very small. When P is very small, all the terms containing P, right, have no meaning. They are zero, right? So that's why it is F divided by square root of, so this term is close to 0, the P is also close to 0, so this means omega square whole square, so omega power 4, that means it can be equated to F divided by omega square. That's the term. All right, and we can also write this amplitude as, we know that there is a term which is small letter f is what we have written, which is nothing but I can write it as f is equal to f by m, correct? So you know that this is equal to, we can write a is equal to, there are other forms in which we can write. So this is, there is a term f by omega square which we have just now found, but I replace small f by capital F by m, right, f by m, that is small f, into omega square. Okay, but what is omega square? Omega square can also be, this is one form I need to remember. The other form is nothing but f divided by, there is sorry, there is a m, and omega square I can write it as mu by m, right? Omega square is this, so m cancels, I am also, I can write the capital A as F by M. Okay, so these are the possibilities. At the same time, I can write the theta now. Also, theta is approximated to, we know that theta is tan inverse of 2bp divided by omega square minus p square. Okay, but p is there in both numerator and denominator, but out of which the numerator is close to 0. This means numerator is 0. So tan inverse of 0 comes into picture, which is equal to 0. So, right, under the condition where the driving frequency, that is P, is less than omega, we have to use these two equations for A and theta. Theta becomes 0. I don't have to calculate, but in any problem to calculate the capital A, I can use the formula F by omega square, or capital F by M into omega square, or capital F by M. F by mu, my mistake, sorry, I'll just make a correction here. So please see this is not M, this is mu. Okay, F by mu. All right, then we'll go to the next case, that is the case number 2. So in this case, we will consider that the applied frequency is very high, that is the p value is much greater than omega. Once again, we'll start with the amplitude, that is A is equal to, this is F divided by square root of, this is omega square minus p square, the whole square, plus 4 b square into p square. Now omega is neglected, you can simply take minus p square the whole square. So, right, the p square still remains. I can write this is approximated to the F. Now omega term is not there, so p is very big, so you can see that F divided by root of, this is p to the power 4 plus 4b square into p square. So the term p to the 4 is much bigger compared to the second term. So we can approximate. Therefore, A is approximately equal to F divided by root of p to the power 4. So that is F divided by p square. So you see the frequency is, amplitude is now changed in terms of A. A is equal to, we can write F by p square. That's the change when p is much bigger. Also, we write the theta now. Okay, so theta is equal to, see, this is tan inverse of 2bp divided by omega square minus p square. So this is something like the denominator is closer to p square, right? So I can write this is approximately equal to tan inverse of 2bp divided by minus of p square, as omega is closer to 0, right? So p will cancel, one of the p will cancel. So denominator p is very big, numerator is small, which means we know that the term, whole term becomes equal to, right, it's a negative quantity, it's a negative and very small quantity, right? So this is, right, approximately equal to, now I can write tan inverse of negative, it's not 0 but closer to 0. So but I don't have any other option, I need to write a 0. Tan inverse of 0 is 0, tan inverse of negative answer closer to 0 will be pi, 180 degrees. So theta becomes equal to 180 degrees in this case. So that is case number 2 of what you call the forced oscillation. Then we have a third condition, that is case number 3. You can see that this is equal to a condition wherein the external frequency equal to the natural frequency of oscillation. P is equal to omega, right? Frequency of the external force is equal to the natural frequency of the body. Right, this implies, let's start with the equation of A. A was derived as f divided by square root of omega square minus p square the whole square plus this is 4 times p square into b square. Now they are equal means what? You can see the first term is, this whole term is 0. So we have, this is equal to, numerator is f divided by, I can write root of 4 is 2, root of p square is p, root of b square is b. Okay, so we'll make modifications in this. This is the first equation, f divided by 2 times p into b. Okay, but what I try to do here is that I will try to substitute the value for f. So I'm going to substitute this value. What is f? Small f is equal to capital F by m. Also, I know that there is a 2b in the equation. 2b is what? 2b is r by m. And also we know that the p value can be replaced as omega value. We are going to use these three in this equation. So this is f divided by m divided by, there is a 2b, 2b is nothing but r by m into into p, sorry, p can be written as omega. So I can see that m cancels. So this can be written as, therefore a is also equal to capital F divided by, it is r into omega. Okay, so we can write in this fashion as well. So also we'll calculate the theta. So theta is nothing but, the basic equation is tan inverse of 2bp divided by, this is omega square minus p square. So denominator is in 0. Something by 0 means infinity. So I have to take the tan inverse of infinity, that is what, 90 degree or pi by 2. So we get an answer equals to pi by 2 here. So that's the answer. So in this case, when p is equal to omega, right, the frequency of oscillation of a body becoming equal to uh, the natural frequency, right? You can call this particular body is said to be, right, in resonance. Okay, this condition, we say that the amplitude of vibrations is a maximum. This means, right, the particular situation is called as resonance. Right. So one of the very important concept in uh, physics as well as electrical electronics is called as vibration. This is in the vibration, the important concept is called as resonance. So even in the mechanical field, automobile field, the resonance is pretty important. Even in case of a civil application, we'll see the resonance coming into picture. Okay, so now we'll go to the topic that is called as resonance. So we need to look at the what is resonance, right? We'll directly write the required definition of resonance. All right. So the phenomenon, the phenomenon of making making a body to vibrate vibrate with the maximum possible amplitude. Okay, with maximum amplitude under the under the influence of an external force, right, and whose frequency is equal to the natural frequency of the vibrating body, right? This particular phenomenon is called as resonance, right? So that is the concept called resonance, and there are many applications we can see. So the one application which we are going to see now is the forced vibration of a circuit, oscillations or vibrations in a series LCR circuit. So first let us write a LCR circuit. So we know that in the field of electrical or electronic, we have three very basic components, and such components have different characteristics and different representation. So one such circuit is what we are going to consider now. So let's say this is a circuit containing the three basic components. Okay, so the components, as you can see here, right, are L for inductance, C for capacitance, and R for resistance. Okay, now let's start the discussion about this, and let's see how the forced vibrations are occurring inside this particular circuit. Okay, now let us say there is a circuit LCR. It is said to be a series circuit only because all the components, inductance L, capacitance C, and R, are connected in series one after the other, and this combination, the series combination, is connected to a AC source, right, which AC source is the external force. So instead of force we have a external power supply. Okay, now okay, first let's write this, then we'll see how the oscillations happen, and we can write even the equations for this. Okay, so let a series LCR circuit is connected to an AC source. V is equal to, say, V naught into sine PT. Okay, so what is the frequency of the oscillation, which is, right, P by 2 pi, because P looks like a omega for me, so omega by 2 pi is the frequency. All right, so when we need we can use it. Now in a series circuit we can calculate the voltage across each of the device and add them to get the power supply voltage, right? So we can write the voltage across L, voltage across C, and voltage across R, right? this implies the voltage across capacitor is denoted by Vc. So Vc is equal to, so if you remember the basic equation, right, the voltage across any capacitor is given by the charge stored in the capacitor divided by its capacitance. So let me call this, say this is equation 1, this particular equation is 2. Also, we can write the voltage across inductor. So I'll show the terms there itself so that it becomes easy for you to trace. Okay, so let us say we have the three components like this, and let's write the voltages across each of the device in the following fashion. Okay, so this is the voltage across capacitor and this is the voltage across inductor and resistor. So we will denote this is VL plus minus, so always there will be a polarity in the beginning. So this is plus minus VC and this is plus minus PR. So they are the voltages across each of the device. Now when you add these voltages, you should get a supply voltage V. Okay, this is what is the convention. Now we are applying the same thing here to write our individual terms. So VL is the voltage across inductor, that is given by L into the current L into di by, okay, so there is another convention. Please remember, when you write a AC quantity, that will be always a small letter, so di by dt. So I is nothing but rate of change of current. So rate of change of charge, sorry, I is equal to dq by dt, rate of change of charge. So I can write this as L into d square q by dt square. All right, so this is what we call equation number 3. Let me even mark a current here. Okay, so this is the direction and let's call that as I. Current is flowing in this direction as of now. Okay, so VL is written, and also let's write the VR, that is voltage across resistor, is I into R. But what is I? I is dq by dt, correct? So this can be written as R into dq by dt. Call this is 4. Right. Now we will apply the Kirchhoff's voltage law, KVL. That is what is called as a KVL. In order to apply KVL, I need to move around the circuit in a specific direction. So I am marking the direction like this. Okay. So that means applying Kirchhoff's voltage law to this, KVL to this, we can see that the supply voltage is capital V minus the first term is inductor, so VL, minus the voltage across capacitor minus voltage across resistor equal to 0. This is what is the term. But what I do, I'll take the negative term to the right side. So this implies, right, I can write VL plus VC plus VR is equal to V. Now let us substitute the values already we have written, right? We know that what is VL, what is VC, what is VR. We just have noted down over here. You can see VC is equal to equation number 2, equation number 3 and equation number 4 as well as equation number 1. So we'll put equation number 1, 2, 3, 4 in this equation to get the following case, right? So I can see that this is now L into d square q by dt square plus r into dq by dt plus q by c is equal to v naught sine pt. Now what we did in the previous example, right, when we discussed the concepts of oscillation, we used to write in this way, right? This implies I divide by L throughout. So you can see that you have d square q by dt square plus r by L into dq by dt plus this is q by lc is equal to, this is v naught by L into this is sine pt. Okay, let's call this by equation number 5. Now let us recall, right, the equation of forced oscillation we studied in the previous section, right? So comparing with let's compare this with the standard equation, that is d square y by dt squared plus r by m into dy by dt plus the mu by m times y is equal to f by m into sine pt. So this is equation number 6, which was already written somewhere else. Okay, now what we have to do here is that we need to right consider and compare the equations 5 and 6 so that you can compare the oscillations happening in a mechanical applications, right, and the electrical oscillations. We can compare the terms. So what happens displacement, what happens to the mass, what is the velocity, what is damping coefficient, etc. We can directly find from these two equations. Okay, so that concept we will do in the next class.